Hello, my name is Ethan Roberts. I am doing the modeling and controller design of a DC motor using a PID controller. First off, what is a DC motor? DC motor has two different configurations, a brush DC motor and a brushless DC motor. A brushed DC motor uses a configuration of wound coils as the armature, acting as a two-pole electromagnet. The current's directionality is reversed twice per cycle by the commutator, a mechanical rotary switch. This facilitates a flow of the current through the armature. Thus, the electromagnet poles pull and push against the permanent magnets along the outside of the motor. The commutator then reverses the polarity of the armature's electromagnet as its poles cross the permanent magnet poles. A brushless motor, by contrast, uses a permanent magnet as external rotor. In addition, it uses three phases of driving coils and a specialized sensor that tracks rotor position. As the sensor tracks the rotor position, it sends out reference signals to the controller. The controller in turn activates the coils in the structure, one phase after the other. The benefits of using a DC motor is that DC motors have a higher starting torque. They also have a quick starting and stopping speed. They also have reverse options. Variable speeds vary with output voltage input. The easier and more cost-effective to install controllers on as well. The uses of DC motors include robotics, tools, game systems, computers, toys, automotive, and aircraft. But they're not just limited to these different categories. DC motors are really commonly used in many different areas of our lives due to the benefits previously stated. In this system overview, we're going to be talking about the design specifications, the system model, open loop response, the closed loop response, and the transfer functions for this system. The system assumptions for this model are that our DC motor is a brushless DC motor, that we're dealing with a rigid rotor and shaft, that we have a viscous friction model, that we have a single voltage input, and our output is angular velocity. The DC motor specifications are from Elwood Motors. For this model, we're using a 4-inch diameter motor, that our rotor inertia is 0.013 pounds per inch per second squared, that our viscous damping coefficient is 0.966 pounds per inch per second over radians, that our back EMF constant is 0.0348 voltage per radian over minute, that our armature DC resistance is 0.84 ohms, that our armature inductance for this model is 3 millihenries. And this is the block diagram of our DC motor that we'll be using to model our DC motor. This block diagram simplifies to K over parentheses JS plus B in parentheses LS plus R plus K squared. Using the inputs previously stated for our motor, the step response was produced for our motor. Currently, our motor settling time sits at 0.0539 seconds. The percent overshoot is at 0%. The design requirements: our settling time has to be less than 0.5 seconds. Our overshoot has to be less than 10%, and our steady state area needs to be 0%. Here's the motor under the root locus with our boundary conditions applied. For our real zeros and integrator, our real poles are located both at -200 and -66.1. Our gain is at 245.6. This is the system response with the PID controller. This was before our PID controller was tuned. As you can see, our percent overshoot is within tolerance. Our settling time is at 0.197 with the current settings. But the rise time is at the response time for this system is at 0.118 seconds. We wanted to adjust the rise time to be able to make it faster at responding. So thus we tuned our PID controller so that since we have such an excess of overshoot and settling time, to increase that response time. As said before, our gain was tuned so to improve our time response for the system. This was done until we reached our limits. The first thing to reach limit was the overshoot percentage, which it finally reached 10%, with our gain being at 382. Our settling time maxed out at 0.241 seconds, which is just short of being halfway to our requirements. But with that in mind, we were able to reduce our rise time to 0.072 seconds, thus allowing our system to respond faster. And this is a system model of the PID controller in the system. In conclusion, with a moderately efficient motor, a efficient PID controller can be developed to fulfill a variety of design needs. This can be helpful for designing and prototyping without needing to do time-consuming trial and error. Even still, all trial and error occurs at the modeling phase of the process to achieve the design specifications, or to improve upon previous unstated specifications. And here are my references. I hope you all have a good day.